Hi, everyone. Thank you for joining us today. Welcome to the last installment of the Simulation Showcase. This webinar is focused on workflow tool and development, and it is presented by the USA, IBPSA-USA EPSI committee. My name is Kate, and I'll be your moderator for today. While we wait for everybody to settle in, here's a quick rundown of what to expect. Today's session will be recorded and available on the IBPSA-USA YouTube channel. If you missed any of the previous showcases, you can watch them on the recording on YouTube now. If you have any issues hearing the presentation, please try calling in by phone instead of using your computer audio. You can participate throughout the session by posting questions and comments in the Q&A at the bottom of your screen. Questions will be viewable by all attendees, and there is an option to submit anonymously if you prefer. I'll do my best to relay your questions live to each of the presenters following the end of their presentation. For those of you who do not know us, we are EPSI. EPSI is the Emerging Professionals Professionals and Students of IBPSA USA. EPSI is a peer-led group under IBPSA USA focused on professionals with less than 5 years of experience in the building performance industry. So we connect early career analysts with resources, networking opportunities, and leadership insights to help grow you in your career. We're always looking for more energy enthusiasts to join us, so please scan the QR code and join the community. This is the last installment of our new webinar series, the Simulation Showcase. This series has highlighted the work of emerging professionals and students using building simulation to tackle challenges like energy efficiency, decarbonization, and indoor environmental quality. We invited students and early career professionals to submit their simulation-based projects. The selected participants will now present a 10 to 15-minute spotlight session, followed by audience Q&A, and our reviewers will assign scores based on our review criteria. Then the 3 finalists will be recognized at SimBuild 2026 in Minneapolis. Today's session is the last in this monthly series, and presenters will now share how simulation helped them develop real-world design simulation solutions. Our topic for today is workflow tool and development. So without further ado, I'll introduce our first speaker.
Hello, let me share my screen.
Jaeha, I'll give you a quick intro before you get started. Yeah. Sorry about that. Jaeha Kim is a PhD candidate in systems engineering at Cornell University, conducting research in the Environmental Systems Lab under Professor Timur Dogan on visual comfort, qualitative metric development, and occupant comfort simulation for the sustainable built environment. Her interdisciplinary training, an MS in systems engineering, an MS in advanced architectural design for Cornell, and a B.Arch at Hanyang University, bridges engineering models with architectural design practice. Her doctoral research integrates environmental psychology, machine learning, computer graphics, and computer vision to quantify spatial quality metrics such as window view satisfaction, visual privacy, daylight quality, and resulting development and visualization of ViewScore.io, a real-time design support tool with a patent filed through Cornell. Her work has been recognized through competitive fellowships and grants, publications and journals including the Building Environment and Lucos, a presentation at international conferences, and future research focused on links between visual environmental quality, health outcomes, and spatial equity. All right, take it away. Thank you.
Thank you, Kate, for the kind and warm introduction. Hi, I'm Jaeha. Thank you for joining me today. Today, I'm going to show you how we can use AI to simulate something that's always been considered unmeasurable, how much people actually like what they see out their windows. A bit of background on me, I trained as an architect in Seoul, practiced at Bao Architects for 3 years, then came to Cornell for my master's and now my PhD in systems engineering. That path from design practice to computational research is exactly what drives this project. In practice, I saw how much we focus on building efficiency and cost, and how little we account for the people actually living inside. Thomas Hathaway put it plainly, buildings driven purely by efficiency and cost minimization are often the ones society tears down, and Cameron Sinclair said the most sustainable building in the world is the one that's loved. Research backed this up. This research from 2023 shows that buildings in the US and Europe have an average lifespan of 71 years, but many are demolished well before they reach their technical limits, simply because people don't want them anymore. If we want truly sustainable architecture, we need to design spaces that people genuinely value. That means accounting for human experience, not just energy metrics. Half the global population now lives in cities. As those cities grow denser, taller buildings, smaller gaps between them. Access to daylight, view, and visual privacy gets squeezed, and this matters more than people might think. People spend roughly 70% of their time at home, and windows are primary connection to the outdoor world. Yet residential environments are far less studied than offices. We don't have good tools or standards for this. That's the gap we're targeting. I approached this in 4 steps. First, collect large-scale human evaluation data, identify consistent trends in what people prefer, train a machine learning model on that data, and then apply the model at an urban scale analysis. Today, I'll walk you through each of these. Current view quality evaluation standards are very limited. LEED has a binary pass or fail system based on the things like outdoor sightlines, glazing transmittance, and view content. The European standard EN 17037 is more nuanced. It rates view across 3 levels based on horizontal sight angle, distance to visible objects, and numbers of visible layers like sky, ground, and landscape. But the critical question is, do these match how people actually experience views? Let me show you why the answer is often no. Here's a real housing project where the architect carefully designed window sizes and positions. LEED said all floor area qualifies, and according to the European standard simulation results, most of the area has failed. But when you look at the actual view image, it's a thoughtfully designed space. These oversimplified criteria miss a lot. We need something better. However, the scale of the challenge is staggering. To test all the relevant combination of the view factors, window dimensions, room types, and spatial conditions, we need to evaluate almost 86 quadrillion scenarios. That's obviously impossible for one research team. So we've built a collaboration across Cornell, UC Berkeley, New Jersey Institute of Technology, and Singapore University of Social Science, with a shared protocol for systematic data collection. Before collecting data at scale, we need to know which experiment method actually works. We compared physical space experiments, virtual reality, and online image surveys across 5 satisfaction categories. The key finding: for measuring view content and overall satisfaction, digital image and virtual reality experiments both work as well as physical space experiments. That means we can scale up data collection dramatically without sacrificing validity. This is the foundation everything else builds on. Using our validated protocol, we collected over 13,000 human satisfaction ratings and built the window view ImageNet dataset. The surveyed response show clear, consistent trend. Large windows with sky views score highest. Small windows facing neighboring buildings score lowest. To extract features from these images, we use semantic segmentation to identify object type such as tree, sky, building, rows, and depth estimation to measure how far those objects are. The pipeline crops to the human vertical field of view. Extract 23 spatial and visual features and feed them into an AutoML workflow using gradient boosting models. We link those features to the human satisfaction scores and train the model. The result? A system that can predict occupants' view satisfaction from a 3D model alone. To test whether our model generalized beyond the lab, we ran an in-person experiment at the Hasbrook Apartments here in Ithaca. 24 students toured 16 views in person. 282 US residents rated the same views online. The ranking of preferred views matched no statistically significant differences between students and US population. And when we look into demographic effects, we found that women rate views slightly lower than men for the same scenarios, and older adults tend to be more sensitive to privacy. These are real design implications, especially for senior housing. We then tested the model in a much more demanding context. 24 residential units across 12 building archetypes in New York City. 66 participants spent 2.5 hours rating views in person. When we compared their satisfaction scores against our model, called View Score, against LEED and European standard, the results were clear. View Score achieves a correlation of 0.68 with human satisfaction, which is higher than LEED and European correlation coefficients. On our validation image dataset, the ML model explained 81% of human satisfaction variance, with only a 9% error rate. For something widely considered immeasurable and subjective, this is a meaningful result. We've packed all of this into ViewScore, a Grasshopper plugin that integrates directly into architects' existing design workflows. Give it a 3D model of your design and context and run the simulation, and it exports predicted view and privacy satisfaction scores. You can visualize the result as a pie chart, heat map, 3D box map, and TensorFlow style plot. The goal is to make evidence-based decisions about window design accessible at the earliest design stages. Finally, we applied ViewScore at the city scale. In collaboration with a New York City property management company, we simulated view, privacy, and daylight across 35 residential buildings archetypes, which is 10,420 rooms in total. The findings are sobering. 71% of rooms have unsatisfactory views, and over a third of floor area has visual privacy issues. Building density is the dominant driver of view and daylight quality, while privacy is largely floor-level dependent. We are using these results to establish evidence-based benchmarks that can inform both design practice and housing policy. To wrap up, what I've shown today is a workflow for turning subjective human experience into a quantifiable, simulatable design variable. We started with views, but this same pipeline can apply to acoustic quality, texture preference, spatial comfort, any qualitative factors that matters to occupants. ViewScore is launching a beta version in early March. If you'd like to test and use our software, please register via the QR code on the slide. And if you're interested in research collaboration or industry partnership, please reach out to me. We'd love to talk. Thank you.
Thanks so much. What a great presentation. I'm curious what the next step is for your research.
So we just finished the urban analysis using the 35 archetypes, and we are actively collaborating with the property management firm. So next step is evaluating how economic value of view and visual privacy and daylight quality. We know it is important, and that we know in the work performance wise and like well-being wise, but we don't know how economically it values and how much people are willing to pay for it.
Yeah, that was kind of what I was thinking about as well. I've been touring apartments myself to find a new place to live, and I'm, really disappointed by how many apartments
Mhm.
have terrible views. Do you think it could eventually, I mean, would you like it to factor into the cost of an apartment, or like how do you envision this kind of integrating?
We're thinking like first it should be posted to the renters and realtors, the view quality, and then they need to think about are you sensitive to view or are you sensitive to privacy? And also it needs to be communicated with the house owners or like a property management firm to help them the exact like a pricing of the unit. So far, the residential unit price is decided by the room type and floor area, and then the floor level. They don't care about, they don't pay much attention on the orientation or view quality or things like that. So we're thinking this analysis could help them, the owner and then also buyer, also realtor, developers, to improve the overall urban residential quality.
Nice. Yeah, it makes a lot of sense. Well, thank you so much. That was super interesting. Anybody, if you've got some questions, feel free to put them in the Q&A or in the webinar chat. And for now, we'll move on to our next presenter.
Thank you.
Mame Cheikh is a PhD student at SESI Line Act Laboratory, affiliated with the doctoral school SMI 432 at ENSAM Paris. His research focuses on predictive and real-time management of building integrated photovoltaics, or BIPV systems. He has developed a simulation tool for industrial BIPV, which is a MATLAB app designer-based simulator that synchronizes high-resolution PV generation time series with industrial consumption profiles. His work combines energy system modeling, artificial intelligence, and decision analysis methods to improve photovoltaic utilization, operational flexibility, and economic performance in smart factory environments. Take it away.
Thank you, Kate. Thank you, everyone. Do you hear my screen?
Yes, we can see and hear you. You're good to go.
My name is Mame. I recently completed my PhD in November. So now I'm an associate professor in Cécile in Strasbourg in France. So today I'm pleased to present to you my BI2PV simulator. It's a simulation tool for the industrial building PV integration. So I'm going to give you a first introduction and present the proposed solution and the simulation result, and finish with the conclusion and the perspectives. So the BIPV consists of integrated PV models in the buildings, and so it enables to produce more energy. And now we are using this PV in every way in the buildings, like in the roofs, facades, and windows. And for people who works on developing artificial models to predict PV systems, it's interesting by having the some PV data sets for this the production of the buildings. For example, in every 5 minutes or 10 minutes, it's very interesting to have this data to develop some models for predictive models. So now I'm gonna moving in the proposed solution. So our simulator, we use many types of data. For example, the models or the PV panels, and the consumption of file of the building, and some meteorological data of the where the building is located. And we also integrate some financial parameters, and the panels dimensions, and to identify also the blocked area. It's where we can't integrate a PV model in the building dimensions. So we're gonna make some processing and sizing here, and to generate the physical optimal capacity and the capacity we need. And we're gonna make some optimization process to have the most efficient cost and the to rank the models to have the best models to integrate in the building. And finally, we're gonna generate a 3D representation of the models in the in the buildings. So we have also many scenarios like if we are in the clear sky and or if, for example, we are in the rainy climatic zone. So. And here we have some illustration to how our simulator works. So we identify all the blocked area, and after that we're gonna uh, so delete this done for this done for the integration of the PV integration. So here we have the interface of our simulator. So here, for example, we have the all the blocked area we gonna give to our simulator to identify the areas we can't, for example, integrate PV models. And after the simulation, so we're gonna have the 3D representation. And the most interesting thing in our simulator is the data set we're gonna have in the end of the situation, and it enables us to develop some AI model to predict the production of the building, and we use this later for some smart energy predictive energy system for strategy system. So here we have a video to show how our simulator works. So here we have the database we have to integrate. So here the meteor database. The, oh, sorry. So here we load the database and for the consumption also. And here we are gonna load also the database for the blocked area. And we run the simulation here. So we can see the progress of the simulator. Yes. So this simulation was developed in with MATLAB app designer. And at the end of the simulation, so we have here the ranking of the 5 or we have 6 best models, and here we have that the 451 is the best one, and we use this to integrate in the simulation. So here we have all the scenarios. Here is the clear scenario. So here we have the real one, and we have others like for example the rain one, and we have here the database of the PV production every 10 minutes for 1 year. And here we have for example, for the real scenario, we have for more than 5,000 panels to integrate or in the roofs and the south facade only. And for the clear, so only the roof were exported and for the rainy. So here we need more panels, and so we use the all the roofs and all the exploited area on the facades. So for conclusion, this simulator were developed in MATLAB design, and we use all the workflow, going from the weather data, we got some scenarios, the models, and the optimization surfaces, and economic validation. So, multi-layer decision framework based on AHP and TOPSI were used also, and for the capacity, so from for the clear sky, so we have for mini modules, so we can go from to 200 and to 2060 kilowatt peak, and for the real weather, so from 200 to 2090 kilowatt peak. So the best compromises for the real scenario is the model 451, and we had a return of investment year of 7 years, and we have also the data set, and this work was published in the Energy and Building journal. And for the next work, so we gonna use the database to develop our predictive energy management in the PV grid systems. We try also to work on this simulator to develop an open source version to enable others to have free access of this simulator. And thank you for your attention.
Thank you so much. Yeah, great job. I'm curious if your tool is going to be available to the public or if it is already.
Sorry.
Is your tool available for other people to use, or is it mainly internal use right now?
No, right now it's not because it's only usable on MATLAB. So if you don't have the license, it's complicated to use this. So we try to develop it to work on it to translate the code, for example, in Python, and to try to use to develop a free version for all the, especially for the students to use it. Yes. And the industrial, for example, if the industrials want to have a tool to know, for example, how to integrate some PV models in their buildings, it's yes, usable. So yes.
Got it. Thank you. Well, great job. Thanks so much. All right, we can move on to our last speaker. Guanzhou Ji is a research associate at Carnegie Mellon University's Illumination and Imaging Laboratory, where his work focuses on 3D scene understanding, image-based rendering, and physics-based simulation. He earned his PhD in Building Performance and Diagnostics from Carnegie Mellon University in 2025, the Robotics Institute and School of Architecture, and was a recipient of the IBPSA-USA Student and Emerging Professional Scholarship. G serves on a national and international committees, including the AIA National Building Performance Advisory Group, the IES Residential Lighting Committee, and the CEI Technical Conference Committee. Take it away, Guanzhou.
Yeah. Thanks, Kate, for the introduction. And here's my talk. Okay, thanks all for joining us. And here's my talk, Indoor Heat Estimation from a Single Visible Light Panorama. And so here's a real-world panorama. So we can see, because it's a single image, and we can see a lot of distortion. And then for this work, I will be presenting, okay, given a single image, can we automatically convert the existing home into a new refurnished scene. And from the left to right, it's from captured scene to edited scene. So it's more like a visualization, and this process, we don't need any commercial software. And specifically for building performance, we care about the absolute light level. So like here, we also care about the illuminance. So from the left to right, we can convert the rendered image into absolute scale. And next, because light also brings heat. So for this project, we also trying to estimate indoor heat from visible light. So we assume all the heat comes from outdoor and comes from sunlight. And we can easily crop the panorama into 2D perspective view and see the whole space from 360 degree. Yeah, next about the background. So for this project, we mainly focus on housing market in the US, especially for the existing homes. So by the third quarter of 2024, we have about over 147 million housing units. And specifically, we have over 4 million existing homes on the market. So in that case, we have millions homes, but we don't have millions architects or practitioners in building performance simulation, right? So we need something easy and simple to estimate the light and heat. So in this case, we focus on image-based tasks, and we are trying to understand what's going on from the image. So let's say here's a single panorama. So what we can get is that we have a lot of existing studies detect the wall corner and generate this shoebox model. It's a simplified model, and all the textures are classified into the wall and floor planners. In the meantime, we have some other computer vision and graphic studies that can classify indoor objects into different categories. Here we can see the door, floor, and the ceilings. They are all labeled in different pixel colors. And then in the meantime, if we could capture a single outdoor image, in that case, we have both indoor and outdoor things. We can estimate the indoor shading layer. In that case, we can estimate the indoor material properties. So in that case, we have a lot of information so far. And then this study, we are trying to build a design and a simulation pipeline, trying to understand the physics behind the RGB image. So for the visible light, the most basic scenario is that let's say we have a shoebox model, it's a residential space, and we have a single window. And then we have outdoor light. The light comes from outdoor into the indoor scene. And then we have different indoor objects, right? Different objects, they have different material properties. In that case, we can shape the indoor appearance using physics-based rendering. So we have to capture both indoor scene and outdoor scenes. That's why we need both indoor and outdoor images. However, for more general case is we have multiple windows. If we just have one single window, we can use a single camera using fisheye lens to capture the fisheye image from the indoor to outdoor. But what if we have one more window opening? So what we could do? So in that case, we cannot just bring one more camera. It will just increase the complexity of the pipeline. So we use a 360 camera named Ricoh Theta Z1. So we capture outdoor scene at different scenarios. First, like for low-rise building, if the window is operable, we can just fix the camera just at the window sill. And then if the window is not operable, so we need to go outside, then capture the outdoor space. And then sometimes for high-rise building, it's common the window is non-operable. So we place the camera near the window. And still, if there's a balcony, super, then we can capture the outdoor space. For indoor, we use mobile app to control the automatic HDR photography. And then in that case, both indoor and outdoor images are captured in HDR format. And then in the past few years, I have captured multiple rooms. Overall, here's just one of the data set I want to show here because indoor image is paired with outdoor image. They are one-on-one paired. And then we almost have 141 paired images. This is a data set and also available for public to access. And the next, if we want to achieve physics-based rendering and simulation, we need to build a full virtual model. So we use indoor panorama to estimate the 3D layout and the material properties. And then we have outdoor image served as the environment map. So using this approach, we build this virtual model, but the interface here is fully virtual. We don't have a user graphic interface like a Rhino or Design Builder to manually edit anything. Everything is behind the scene at the back end. And then we place different virtual objects and virtually render the new thing with new furniture objects. And then because we care about the physical meanings behind the RGB pixels, so we estimate the light and the heat after the rendering. So for indoor light estimation, the workflow is, okay, we have a single image, we estimate the geometry, light, materials. And here is important to note, for now, this study, we assume the materials are Lambosian. And then we output a new rendered image. And we could estimate the light map. For the heat estimation, the thing is that if we have a single RGB panorama, we have achieved virtual staging. But what if we can have another panoramic image can tell us, okay, the outdoor temperature is high, should the window be closed, or how much heat on the wall? And still the floor is carpeted, how much heat would a wooden floor accumulate? Because the light brings the heat, and to estimate the heat, we follow this pipeline, and for the heat, we have different components for the heat transfer, like radiation, conduction, and the convection. So this is the mathematics and the fundamentals behind the heat equation. So we have conduction, convection, radiation, and absorbed heat flux. So the T is the temperature, will be changing with the T, which is the time. So in that case, it's not that simple because in the real world scenario, a single room could be at a rooftop or in the basement. In that case, we can also customize, okay, if there is a heat transfer between indoor and outdoor. If it's in the basement, we assume the heat transfer is minor. But if it's at the rooftop, we get a lot of heat from the sunlight. So we further modified this equation, and then we incorporate indoor-outdoor heat transfer into the simulation. So in that case, we can simulate the real-world scenario here. Okay, let's say we have a single RGB image. We estimate the geometry, material, and light. And for the right, we just view the 3D model from the top view. And it's also important to note, okay, the 3D layout comes from the layout estimation. Sometimes the wall corner is not 90 degrees, so that's a limitation of the layout estimation. But overall, we can estimate transient heat from a single RGB image. And this is a demo video, so we can view the space from 360 degree. And we also tested different rooms. So from the panorama, we can always easily to crop that into 2D perspective view. And as always, because the area near the window always receive more light than other areas, so we can see more heat generated near the window area. And next, because we can also use image-based rendering to change the outdoor image. So once we change the outdoor image, we can estimate different indoor heat at different times of the day. So the application is we only need to go to your house just once, then we can estimate the sun position at different times. So for virtual home tour, we don't need to ask a housing agent to visit the house for multiple times, which is not efficient. And here's another view if we look at the result from panoramic perspective and see how the sun changes. And we also developed some software application for interior design. So for most of the cases, the indoor space is furnished And normally it takes a lot of time and effort to clean up the furniture, or we if we hire someone to clean up the room, it costs money. So we develop image imprinting algorithm that can automatically detect the furniture objects and automatically remove the indoor objects. It's a simplified process, but we still can some leftover for the shadow. And in the meantime, we can place our preferred furniture. Like here, I just placed some IKEA-styled furniture. So we place a new furniture objects into the existing home. And then if we want to change the furniture layout, so we need multiple things. First, furniture objects, floor mesh, and we want to know the orientation and the location of the furniture objects. So, but for this work, we automatically detect where the window is and using two different parameters, distance to window and the distance to wall to control the location of the object. At the end, we output the adjusted furniture objects. So in that case, we can control the furniture objects and especially control multiple furniture objects and their locations within the space. So for physics-based rendering, we also need the material properties. So we can customize different materials for different objects and then achieve virtual home staging. And then, as I mentioned, we can easily change the materials. For example, we change the floor materials for this space. And also because we have a full virtual model and we have a full virtual render, we can easily have a virtual home tool, change the view space and move into different locations. And because we have outdoor image, so in that case, we can see what's going on in the outdoor. So maybe you prefer the first room, but if I tell you there's a gas station outside, maybe you would change your mind. And then for the second room, looks a little bit simple and but if I tell you you have a big open wide view, maybe you are more likely to purchase this home. And here's the application. If we can change the outdoor image and then customize the sun position, we can simulate the light in the indoor space at different times of the day. And sometimes when we visit the house, it's not always sunny or not always cloudy. So if we capture an outdoor image based on the GPS location and the camera pose and the times of day, so we can find where the sun is on the 2D image. And then we can easily choose, okay, let's wipe out the sun and see how this space looks like under overcast sky. And for this room, when I visit the house, it's cloudy, and it's always nice to see the sunlight. So in that case, I add a virtual sun here. So once I change the sun position at a specific time points, we can see how this space looks like during the day. And we also care about the night. In the evening, we don't have the light from outdoor. We have light source in the indoor space. We can place a light source, artificial light source in the indoor space. And for physics-based rendering, we also added different lighting fixtures with different color temperatures. And we can see here, so if I increase the color temperature, we can see more and more bluish tones. Yeah, next, to summarize this work, so this work will achieve this pipeline. So we have indoor plus outdoor images. Then it takes a few minutes so we can achieve a virtual home staging and analyze the light and the heat. And overall, this is the pipeline. We have captured the image as the input. We output edited scene, and then we can use this tool to do lighting estimation and heat estimation. And at the end, for the acknowledgement, we would like to thank Zillow Group for providing a small gift for this work. And this work was supported by NSF grant. And thanks all. Here's my, that's all my talk.
Nice job. Thank you so much. Um, Similar question that I asked earlier. I'm curious what your next step is for this
Yeah, that's a
research.
good, yeah, that's a good point. So for now, we use 360-degree camera, recall Theta Z1 a long name, and we realize it's still a little bit pricey because the price is about $1,500 each, $1,500. And then for the next, we hope to use mobile app because everybody has a smartphone nowadays. If we can capture limited indoor images or capture a video, could we achieve this kind of virtual staging pipeline? In that case, I mean, if we simplify the workflow, means we need to deal with more errors and all those things. But I think that's the next stage, next direction. Yeah.
Nice. I'm also curious. It sounds like your research and Jaeha's research, like there are definitely some synergies there. Had you guys heard of each other's research before? Have you guys collaborated at all?
Guangzhou,
Uh,
please explain about the
yeah, that's
internal
a good point.
relationship.
Yeah, that's a good point. So previously, uh, I I read her work, her paper, all those things. Then we just connected to each other. It's always nice and connect to peers in this building simulation community. Yeah, we also would like to connect more people. Yeah.
Neat. Well, I'll share my screen one more time and just let you guys know about some additional events coming up with IBPSA USA. So we've got two upcoming online events that you're welcome to attend. The IBPSA USA Career Connections will be on February 27th. So I think that's coming up next week. It'll be from 9 a.m. to 2 p.m. And so that's a virtual career fair. And then we've also got a Project Stasio webinar that Guanzhou is helping with, helping organize. So it'll be visualizing building performance with game engines. So that'll be led by Patrick Peace and um, Eric Naarhi. Excuse me if I pronounced that wrong. And then lastly, we've got our SimBuild coming up in May of 2026. We've got registration open for that right now. We've also got a handful of pre-conference workshops you can attend. So with that, thank you so much for coming to the webinar, and feel free to catch up on the Simulation Showcase webinars you missed virtually on YouTube. Thank you. Have a great rest of your day. Bye.
Yeah. Thank you.